Good morning, everyone. I am Cheryl Lamambas from Kaswagan, Sibaga, Tagusan del Sur, and I am BSED 3A. My topic is all about high-energy particles and accelerators. So what are high-energy particles? High-energy particles are very small particles that move at extremely high speeds, close to the speed of light. This particle includes electrons, protons, and other subatomic particles. Scientists studied them to understand what matter is made of and how forces work at the smallest level. Because these particles are so tiny, we cannot see them directly. Instead, scientists use high energy to make particles collide, allowing new particles to form and be observed. Next is all about fundamental particles and interactions. So we have elementary particles of the Standard Model. The Standard Model of particles physics classifies all known fundamental particles into two main groups. One is the fermions or matter particles, and second one is bosons or force mediators. So fermions or matter particles, these particles make up matter and obey the Pauli exclusion principles. We have here the quarks. Quarks are the building blocks of protons and neutrons. They never exist alone. They always combine with other quarks. They interact through the strong nuclear force. Leptons. Leptons are particles such as electrons and neutrinos. They do not feel the strong force. Electrons are important in electricity and chemistry. Another fundamental particles is force mediators or bosons. These particles that carry forces, example photon or electromagnetic force, gluon, strong force, and W and Z bosons are the weak forces. So why do we use particle as the accelerators? So a particle accelerator is a machine that speeds up particles using electric and magnetic fields. The faster the particle moves, the more energy it has. Particle accelerators are used to break particles apart to see what they are made of, create new particles and energy, and study fundamental forces. An example of particle accelerator is the Large Hadron Collider or LHC rather. We have here the purpose of particle accelerators. So particle accelerators are designed to increase particle energy to relativistic levels, control particle beams precisely, enable high-energy collisions for experimentation. These collisions convert kinetic energy into mass, producing new particles according to Einstein equations, which is the A is equals to mc squared. Another is a type of particle accelerators. First is the linear accelerators or LINACs. So linear accelerators are particles that move in a straight line using oscillating electric fields and used in research and medical therapy. Number 2 is circular accelerators. So these particles travel in circular path using magnetic field, allow repeated acceleration. Example, the cyclotron, synchrotron, and the Large Hadron Collider or LHC, the world's most powerful accelerator. Next is the interpretation of experimental result. So when particles collide at high energies, number 1, we have the collision products are detected. So which means detector track particles path, energy, momentum, and charges. Example, calorimeters, tracking chambers, and muon detectors. Number 2 is identification of particles. Curvature and magnetic fields reveals charge and momentum. So when they identify particles, the energy loss patterns identify particles types. Number 3 is the inference of fundamental properties. So we have the quark structure is inferred from jet patterns, and leptons are identified by clean penetrating signals. Force mediators appear as resonance peaks in energy spectra. Number 4 is the verification of theoretical models, which means experimental data are compared with predictions from quantum field theories. Discovery of particles, example Higgs bosons, confirms theoretical frameworks. Those experimental observed allow physicists to determine particle masses, interaction strengths, symmetry principle, conservation laws. Another is the technological requirements of particle physics. High energy particles physics requires advanced and highly specialized technologies such as accelerator technologies, which means superconducting magnets, radio frequency, cavities, and ultra-high vacuum system. Number 2 is the detector system, which means precision silicon sensor, scintillators, and calorimeters, high-speed data acquisition electronics, and number 3 is computing and data analysis, which means massive data storage system, distribute computing grids, and advanced algorithms and AI-assisted analysis. Cryogenics, which means liquid helium cooling for superconducting components and operation at temperature near absolute zero. And lastly is the technology transfer to society. So technology develops for particles physics have significantly benefited society. So number 1, we have the medical applications for cancer, radiotherapy using particle beams, PET and MRI imaging technologies, and hadron therapy for tumor treatment. Number 2 is information technology for development of World Wide Web at CERN, and also advance in big data processing and cloud computing. Number 3 is industry and engineering that conclude superconducting materials, precision manufacturing techniques, radiation detection, and safety system. Number 4 is security and environmental monitoring, which include cargo scanning system, radiation monitoring, nuclear safeguards. So these applications demonstrate how fundamental research drives innovation beyond science, improving health, communication, and technology. High-energy particles physics combines theoretical insights, experimental precision, and advanced technology to explore the deepest structure of matter. Through particle accelerators, scientists interpret experimental results to understand quarks, leptons, and force mediators, pushing the boundaries of human knowledge. At the same time, the technological advances developed for this field continue to provide profound benefits to society.